Okay, while you're probably still working on it, I'd like to give an overview of the results. And so first of all, as usual, I should say, whenever you do something to a Markov state model and you want the kinetics to be correct, the spectrum or the eigenvalues and eigenvectors are important. That's always the basis for reproducing the long-time dynamic. So this slide you have already seen, so I'll just skip over it. Now, PCCA, you've also seen. Basic idea is the following. We have a transition matrix, the large transition matrix with many states, and that has eigenvectors and eigenvalues. And we are only looking at the first few of them, let's say 5 or so. Ideally, if there is a gap in the spectrum that tells us how many we want, otherwise you might say, okay, I'm interested in resolving timescales of at least this value, and that defines your cut. Okay, so you will have a number of eigenvectors here, and those eigenvectors then define your coarse graining. This is very similar in idea like principal component analysis. Yeah? In principal component analysis, you compute this covariance matrix, which tells you something about the variances in the data. You look at the dominant eigenvectors and you project your data on it, and you restore the maximum variances. In TICA, you do something very similar with time-lagged covariance matrix that maintains your slow processes. In PCCA, it's very similar in the idea. You compute the eigenvectors of the transition matrix and you somehow project on them in order to get a model that is coarse-grained or has only a few states. Now, PCCA is an algorithm which takes these first few eigenvectors and transforms them into another matrix. Essentially, this transformation is just a basis transformation. So it takes vectors and it rotates them around to a new basis. And in this basis, these vectors can be interpreted as memberships. So as a degree of each microstate, each cluster of the MSM belonging to one of the 5 metastable states. So it's giving you a probability, or the probability that a microstate would belong to a certain macrostate, or vice versa. You can compute the probability that a certain no, that's right. That's the conditional probability that given you are in a certain microstate, you are belonging to a certain macrostate. So it's a fuzzy clustering. So now we can take it from here and say we want to just coarse-grain this clustering by saying at each microstate I'm asking what is the macrostate, the metastable state that I belong to most, and I just assign the state to that. So you just use this fuzzy clustering to produce a crisp clustering. And that would define a coarse-grained Markov state model. Now that is pretty bad, because what happens is, remember, it was important for the Markov state model to approximate these eigenfunctions here well. And we needed many states in order to approximate this form well. Now, if you do a hard clustering by saying, okay, everything which is on the left here belongs to state 1 and everything on the right to state 2, you're back to the same situation where you would have just used 2 states for your Markov state model, because now you're approximating this function just with a single step. So, well, you will get an assignment that is meaningful in the sense you have grouped states to metastable states, but the kinetics of this matrix will be pretty bad. The timescales will be too fast. The rates will be too high. Okay. So let me go through this and come back to it later. Now, okay, so first of all, this assignment nonetheless defines a grouping of microstates. So with this you can visualize structures. So you can, for example, sample MD frames from these macrostates and overlay them, for example, in VMD, and that gives you an impression of what are the structures inside these different macrostates. There are some computations that you can do on this coarse graining, on these macrostates, that does not have this problem of messing up the timescales. One of them, for example, is compute fluxes or transition pathways, and Fabian will tell you about that in the next session. So that's what you see here. That's basically the probability flux of going from this state to that state, and that tells you what are the pathways, what's the mechanism in going from this state to that state, and what are the intermediates on the way, and with what probability would I choose this or that pathway if I do binding or folding or conformational rearrangement like here. Okay, coarse graining the transition matrix in such a way that you have few states and the right kinetics, that's difficult. So there is one recipe which was proposed in this paper here by my colleague Markus Weber, who is in the Zuse Institute over there. And it takes a while to understand why this is the right rule, but you can compute the coarse grain transition matrix in this way. So this is the fine grain transition matrix, so the large transition matrix of your Markov state model that you have estimated. And this here is the membership matrix. So that contains the probabilities with which each microstate belongs to a macrostate. So that's a rectangular matrix which has as many rows as you have microstates and as many columns as you have macrostates. So for example, 100 by 5. So this operation here, MTPM, will produce a small transition matrix. And this operation here is needed in order to scale it in the right way. The result of these operations are a coarse grain transition matrix and a coarse grain equilibrium probability vector, which have a few nice properties. So first of all, you can show that this operation will preserve the dominant eigenvalues. So this coarse grain transition matrix will have the same timescales. The same as if this, let's say 5 by 5, it will have the same first 5 eigenvalues. That means the 1 and then 4 eigenvalues smaller than 1, and the 4 slowest timescales will be the same as the large transition matrix. That's nice. That's exactly what we want. Also, it preserves probability mass. So each rows of this matrix sums to 1. So no probability is lost or created. That's already a nice thing. But there's no guarantee that it will be actually a transition matrix because it can have negative elements. And now that's a bit annoying when you're not a mathematician and you would like to interpret your results physically, right? So it has two nice properties, but it really destroys something that we would like to have, namely that this is actually, this contains elements that we can interpret as transition probabilities or rates. That's not possible. Okay, and unfortunately this problem is fundamentally unsolvable. We have to give up something. Either we give up physical interpretability of each single element. We can still use this matrix to propagate probability vectors. There's no problem with that. Every probability vector that we insert and propagate with this matrix will give a meaningful evolution of probability vectors. But we cannot simulate the matrix. Yeah? We cannot sample transitions by starting in a certain state and then asking where do we go next, because what do we do with the negative elements? Or alternatively, we say, okay, I really want a physically interpretable transition matrix, but then I give up some accuracy. So I allow my timescales to be a little bit smaller. I have to decide. Both is not possible. Okay, so that solution is giving me the right timescales, but an uninterpretable transition matrix. If we want, if we somehow want both, if we want an interpretable transition matrix, but also want the right timescales, we have to simply go to a completely different model. We have to forget about Markov state models. And one alternative to that is to do a hidden Markov state model, or a hidden Markov model. A hidden Markov model is the following idea. So it says instead of describing the dynamics of the system as a Markov chain on these microstates, we're saying there is a Markov chain between metastable states, let's say between the 5 states that I want to have. And whenever I'm in one of these 5 states, I have a certain probability of being in one of the 100 states. So it's the same construction like this PCCA coarse-grained Markov state model, but it takes a different viewpoint. It says the Markov state model is in the hidden space. This is between some metastable states. And they have a mapping to what I observe through the clustering. And then I need to learn both. I need to learn the transition matrix, the hidden transition matrix, and this mapping from the data. So it's a different estimation problem. And this is implemented in PyEMMA as well. In the MSM package, there is an MSM estimate hidden Markov model and timescales HMM, I think, to estimate for different lag times. And this model is in principle non-Markovian. It is Markovian in this hidden space, but in the observed space is non-Markovian. So it can describe an evolution which is not Markovian in the observation space. These are some details about the estimation procedure that I will not go into now in detail. But it can be shown. No, this comes later. Okay. But so it can be shown that a hidden Markov model also approximates the right timescales, at least in the limit of good statistics. Okay, so let's look at the performances of these two approaches of this example. So this is our double well system. This is the trajectory generated for this double well system. We have stored a transition matrix in PyEMMA that you have loaded in one of the first few lines of your notebook. And then by saying, give me a trajectory of that length, you sample this transition matrix. So you use this transition matrix in order to generate a trajectory from it. And then you insert it into a Markov state model estimator in order to regenerate a Markov state model. Now, in between these two is a random realization, the trajectory realization, which has a finite length. So these are not necessarily exactly the same, but in the limit of a long enough trajectory, they should be the same. So if the trajectory is pretty long, they should be approximately the same. So here you can see, given such a trajectory, you can estimate this transition matrix. This is just a contour plot of the elements of the transition matrix. But this here compares the timescales of the true transition matrix, so the one that was used to generate this trajectory, and the estimated one. It's a bit hard to see. There is a bullet, a gray bullet, and there is a black cross. So in the first few timescales, these match very well. And then there are a few here where they don't match. And this is essentially statistics. If you use a certain lag time for the estimation, then typically you will not be able to match all of the timescales, especially not those that are faster than the lag time. You will generally lose this. Usually we're not interested in the fast stuff anyway, so that's not so important. Anyway, this estimation is pretty good. If you have used a shorter trajectory, it will be not quite as good in your case. This is the stationary distribution of the Markov state model estimated from the trajectory. This is the first eigenvector, that's always 1, and this is the second eigenvector, which shows this characteristic switch between the two wells. Okay, now we should have. Okay, the title is wrong. This is actually the coarse graining from PCCA. So I take this Markov state model and do PCCA on it with two states, two metastable states, and ask what are the assignments of each microstate to each of the two metastable states. And this is what I get. So this is again the stationary distribution, the same left and right. This is the membership. So this shows you for every of these 100, actually around 80 states, what is the probability with which it belongs to one of the two metastable states, so to either side of the potential. And you can see that it's clearly assigned when you are clearly on one side of the barrier, but in this barrier region, it's fuzzy. So on the transition state, it's 50-50, clearly, but then there's a considerable region where it's uncertain to which basin you belong. And the higher the barrier will be, the steeper this function will be, and the clearer this assignment will be. If it's a very shallow barrier, then these functions really flatten out. You could ask the inverse question and say, if I'm in a certain metastable state, with what probability will I observe the process in one of the 80 microstates? That's this probability density. These two can be transformed into one another. And here you will see if I'm in metastable state 2, then I will be in one of these states here that are in this basin. And I will basically produce this part of the equilibrium distribution of this basin. But because there is a certain uncertainty in assigning states, there is a little bump here too. And that's not so nice. That's a kind of a problem with PCCA. There are different ways to implement PCCA. There are these three algorithms have been proposed to transform the eigenvectors into this assignment matrix here. And depending on which you choose, you get either a more clear-cut assignment, or again, you get physically interpretable memberships, which are between 0 and 1. We have chosen to implement the version that gives you physically interpretable memberships, but it doesn't always give you a very clear-cut assignment. But again, that's a fundamental problem. You have to choose between different benefits and disadvantages. You cannot have everything. Okay. Now, if we use a hidden Markov model, this is the result. So these are the memberships, and these are the probability densities. Now they are very nicely clean. So there is no extra bump here, and these assignments are a little bit steeper. Let's look at the results. So this is the exact time scale of the underlying transition matrix. The black line is the time scale estimated by this large Markov state model with 80 states, so that has no discretization error. It's perfect apart from statistical error. So for a long trajectory, these will be identical. That's just the check. And the blue line is the timescale estimated by this two-state hidden Markov model. So two metastable states and an observation space of these 80 or whatever states. And you see it converges approximately to the right value. It is not exactly right. It is slightly overestimated. And it is correct in the limit where you have high barriers. So the hidden Markov model gives you the correct estimate in the limit where your metastable states are cleanly separated. If you have very flat barriers and everything is very diffusive, then the HMM may give you wrong timescales. But in general, they're pretty close. And the nice thing is you get really a good estimate with 2 states. If you try to coarse grain your PCCA memberships to a 2-state MSM, it will be really crappy. So it will be very hard to get something close to this. So you will need much longer lag times, for example, to get to that region here. Okay. Why is there still an error for small lag times? That is because the hidden Markov model requires this separation of slow and fast timescales. And although this is very much a 2-state system, it's never exactly a 2-state system. There is this slow timescale, and then there is a large gap, but then there are also other timescales, which are the local oscillations within the basins. And since we cannot describe these with a 2-state model, they will cause an error. And that is exactly the error that you see here. And this is actually a multi-exponentially, so that's an exponentially decaying error term. And the exponents are exactly the timescales that you have neglected. So the ones after the first timescale in this case. Okay. Now, where is my mouse here? No, wrong screen. Here it is. Yeah. Okay, so let's just compare Markov state models and hidden Markov models in cases where well, let me go directly to this case. Let's compare their abilities to deal with discretization that is not so good. In practice, the ability to do a very good discretization is limited by, for example, the dimensionality of your space. If you simulate macromolecules, you have a pretty large space. And even if you use TICA and project it down to 10 or 20 dimensions, you still have a pretty large space. So it's very hard to ask for a very, very good discretization there. So your clusters are kind of coarse if you do something like TICA plus k-means or so. So this is why it's very important if we do Markov state modeling that we have this lag time by which we can kind of kill the fast processes and that allows us to work with relatively coarse discretizations. And we don't need to discretize everything very well. But so in this example here, let's look at how Markov state models and hidden Markov models behave if we do a bad discretization. So again, we have the two-world system, but now we coarse grain it by saying I assign these 80 or so states into 6 states or into 2 states. And in the 6 states are a good discretization, and this 2-state discretization is very bad. I have chosen the dividing surface between the 2 states to be not on top of the transition region, so this is a really poor discretization. Okay, so we have data for that and estimate a Markov state model. First of all, these are the timescales of the Markov state model for different lag times. And you see for the good discretization, we converge to a flat region here, which is a good approximation of the true timescale. And for the bad discretization, it's pretty bad. The timescales are too fast, they don't converge. It would take you much longer lag times until you get here. And in fact, you need to use lag times that are longer than this timescale itself, and then you lose the process. So at some point, this curve will just go crazy because you're essentially just trying to estimate noise at some Okay, you can do a Chapman-Kolmogorov test. I don't know if you have looked at that yet. So there's an option CK test in both Markov state model and hidden Markov model estimators that basically take the model and they predict the evolution, the time evolution, for multiples of the lag time at which you have estimated the model, and it compares that with trajectory statistics. So it takes the model at tau, asks what would my model produce if I started the probability distribution in one of the metastable states and evolve it by time steps and tau. And then for each of these longer time steps, it does a new estimation from the data and compares the results of these two. So if everything is right, these two should agree within statistical error. And so for the good discretization, you can see that this works very nicely. So this is the prediction for starting in state 1 and what is the probability to be still in state 1. This will converge to 0.5 because in equilibrium there's 0.5 probability on either side of the barrier. And here this is starting from state 1, what is the probability to be in state 2? And here 2, 1 and 2, 2. So the black is the estimate at these different lag times. The blue is the prediction from the MSM estimated at a short lag time. That's the first dot in this plot, basically. And then the shady region is the uncertainty. So that's a very nice agreement. For the bad discretization, this doesn't work. It's perfect for lag time 0 because it's trivial, then it's always 1, 0, 0, etc. It's also perfect for lag time 1, but it's trivial because an estimate of the transition probability at that lag time is of course a perfect prediction for the same lag time. But then if it comes to future predictions, the two curves depart, they disagree. So this is an indicator that your model is not a good model of the long-term kinetics because the discretization was not good enough or the lag time was long enough for this discretization. Yes?
So the 100, 200, 300, 100 times the lag time, 200 times the lag time, what does it mean in nanoseconds?
It means an original trajectory step. So here, let's see. Okay, so the model was estimated at 40 steps, and then these are 100 steps. So step means the trajectory steps. So this is where the estimate was done, this point here. So these are like 10 steps of prediction. Okay, using the hidden Markov model.
So the model was good until 40, where it was estimated.
It's always good until its own lag time.
Okay, the lag time was 40.
The lag time was 40, that's okay. This number here. But it doesn't do a good job in predicting, for example, 80. Whereas this model does. Now you do the same with the hidden Markov model with the two discretizations, and then you actually get a good approximation of the dominant timescale. And you get approximately converging timescale even for the bad discretization. That is because you do not ask the model to be Markovian in this discretization here, in this bad discretization. So you have a way of saying there is an underlying two-state dynamics, and there's a transition matrix for that, which has a certain timescale. And whenever I am in one of the two metastable states, I have a certain probability of observing the system in one of the two clusters. And even though these two clusters were badly chosen here, it doesn't matter that the dynamics is not Markovian in these clusters. You can still estimate the probability if I'm in metastable 1 that I appear in this cluster, or I have a metastable state 2 that I appear in this cluster or in this cluster. So this learning this assignment matrix separately from the transition matrix allows you to sort of unscramble a poor clustering. Okay, now we choose for example, to build a model at a lag time of 5, so that's shorter than the MSM lag time before. And I'm still very good if I had used a good discretization. I'm better but not perfect in the bad discretization, but that's because at 5 I'm really not converged here. So if I would use maybe 10, then also this prediction would be good. So bottom line is, even if I have a bad discretization, then maybe a hidden Markov model can still give me a good estimation. And I can generally use shorter lag times than I need for an MSM. But I have to choose an additional parameter, which is the number of states, of metastable states, right at the beginning of the estimation. And only if there is a timescale separation between that many states and the rest, so if my system is somehow metastable, this will be a good model. If my system is not metastable, if I would have a multitude of similar barriers and I would still try to use 2 states or so, I would not get a good model and probably not converging timescales. Okay, yeah, that's basically it. So give a try to hidden Markov models. If you get nice estimates and you can validate them with your Chapman-Kolmogorov test, then you have a nice small state model of 5 or 10 states or whatever you used, and that's much easier to interpret than a MSM with 100 or 1,000 states. But the estimation takes much longer. That's the downside, so it runs a while. Okay, thank you.